Hello, my name is Kelly Beltrán, and now I'm going to talk about the analysis of the diffusion process of nitric oxide oxidation in the presence of a platinum catalyst. So first of all, we got our objective, which will be to analyze the influence of two input variables that are the temperature and the concentration of nitric oxide in an oxidation system that uses platinum as a catalyst from a parametric study made in Python in order to choose the optimal operating conditions. One of the biggest causes of the environmental pollution is the emission of nitric oxide gases. In order to reduce this concentration, several methods are applied, such as the selective catalytic reduction, which has a higher efficiency than the other ones. This uses ammonia to decompose the nitric oxide into water and molecular nitrogen. However, there is a key step in this process, which is the conversion of nitric oxide into nitrogen dioxide in the presence of oxygen, and uses a metallic catalyst in this process. So in our study, we use platinum, which is a wire of 25 micrometers of radio and a long of 3 millimeters. At the beginning of our system, we have a concentration for the nitric oxide of 540 ppm, and at the end, we got a conversion of 85%. Since the length of our wire is greater than the radio, the chosen system is a cylinder. The reaction is the one that we got on the screen, is a third order reaction, and based on this sketch, we establish the following assumptions. This is steady-state system, since everything that we got at the beginning is the same as we got at the end, and there's no variation over time. It is a one-dimensional mass transfer related to a rectangular coordinate system on the z-axis based on the diffusion path. The reaction is heterogeneous, controlled by diffusion and reaction kinetics. Since the reaction speed of this is a normal one, and the conversion obtained is 85%. The diffusion coefficient will remain constant along the diffusion path. Now, based on the fixed law of diffusion, we have a relation based on the stoichiometric ratio on the reaction that we got at the previous slide, and we use this equation to determine the concentration profile on the continuity equation. In this, we got two constants. In order to determine the value of those constants, we use the following equation to determine the mole fractions, since the concentration for the nitric oxide used are on ppm units. So those are the boundary conditions. And finally, we got a concentration profile, which is evaluated on Python in order to study the behavior of this reaction. What we got here is that the concentration of nitric oxide decreases along the diffusion path, since this reaction is for a decomposition or oxidation of nitric oxide into nitrogen dioxide. On the fixed law, we got the following. The operating conditions are a pressure of 180 and temperature of 200 degrees. Based on the boundary conditions, we got a molar flux for each component and the stoichiometric ratio used on the fixed law. Now, for the parametric study, we needed an equation to relate the temperature and the time. And we used the definition of the molar flux to compare both variables. The range chosen for the temperature is between the 200 and the 500 degrees, since the reaction is reversible over these temperatures. And based on the graphic, we got as the temperature increases, the time increases. This means that the conversion is lower. Now, based on other studies, we got that the use of supports is very efficient to promote the oxidation of nitric oxide, but at temperatures that are higher than the ones that we have worked in this study. And the parametric study help us to determine the optimal operating conditions. As the temperature increases, the reversible reaction is promoted and the time increases too. This means that the conversion of nitric oxide into nitrogen dioxide is lower. And the increase of nitric oxide at the beginning of our system can help us to improve the reaction time. So, in conclusion, the optimal operating conditions for nitric oxide are at the atmospheric pressure and a temperature of 200 degrees, with a concentration between 500 and 540 ppm. Those are the conditions that we have worked for this system, and based on the parametric study, we established that we obtain better conversion for the nitric oxide into nitrogen dioxide. Thank you.